Hi everyone, my name is Winnie, and my colleague Robert and our boss Phil is sitting there. Today we will give a very brief introduction about the packaged converter module with silicon carbide MOSFETs. Yeah, first I want to say the packaging technology is essential to the high performance of the transaction inverting EVs. And in this presentation, first I want to talk about what are the demands for silicon carbide MOSFET module using EV drivetrain, and then we will give a brief overview of the important stage of making silicon carbide power modules. Okay, what are the demands for silicon carbide power module using EV trains can be shown in this presentation. It is well known that compared to silicon carbide devices can have higher power density and switch faster. To fully utilize the merits of silicon carbide power MOSFET, firstly, we want a more compact design of the packaging to achieve high power density. And this can be done by reducing the size of the packaging. As you can see on the right-hand side, there are two silicon carbide devices are placed on a DBC layout that are originally designed for IGBT, so there are large redundant area. It's not only because the silicon carbide die is smaller, but also the body diode are potentially replaced by the potentially replace a freewheeling diode that must be paired with the IGBTs. And then it can have better thermal conductivity will be required for the further improvement of the power density. And this can be achieved by using more advanced diode touching technology, like a serial sintering to replace a conventional solder material. And finally, we want the module to have a lower string inductance in order to have high switching frequency. This can be achieved by optimizing the layout of the DBC, as shown here. Yeah. Next. Okay, so today I will go through a step one by one. The first is about our simulation study. Why it's become this? Sorry, I don't know. But anyway, so before any actual hard work, simulation is very important as we need to do, as a simulation can help us to have a better understanding of what we can do to reduce the size or what we can change to reduce the street parameters. This is an example of the street parameter simulation based on ANSYS Q3D workbench. Yeah. And then we will induce all the parameters into LT space, another software, to do a single switch event. From these results, we can see the lower the street inductance in the module, the higher the switching frequency can be achieved. Okay, and after a lot of simulation and optimized design, we finally got our final optimized design. This one is the first version we got, it's a non-optimized one. And because of copyright reason, we cannot show our optimized design here, but what I can show is the simulation results and the comparison between them. This figure shows the street inductance between the positive and negative connector of both the non-optimized design and our optimized design. Apparently, we reduce the street inductance to about a third or even further compared with the previous one. So a large reduce of the street inductance, which means higher switching frequency. And okay, sorry. Actually, my presentation is not like this. I don't know what's. I have some further information, but sorry about that, but I will try to carry on. So that is about the preparation of the, after a simulation, we know what we can do, so we can order our own DBC board, and then we can do some preparation before the actual packaging procedures. So first, maybe. So first, if you need to have a DBC. First, if you got some DBC like this, very dirty on the surface, shining, you need to polish it first. So this is all the step I go through to polishing a DBC. And then you need to deoxide, and then you need to put it into a sulfuric acid for 5 minutes and wash it by deionized water for another 3 minutes, and then let's take an ice-no US bath for another 3 minutes. It will become very shiny, like a mirror, as shown here. This is my hand. So I know it's not clear, but dirty one, and after all steps, shiny one. Okay, next step is a dye attach and dye shear test. In the left-hand side is a reflowing oven used for the dye attachment. And in the right-hand side is a date for solvent, which is used to do the shear and wear pull test. During our experiment, we tried different reflowing centering procedures. We reflowing silver center procedures, and for both dye attachment and connector attachment. Finally, we found our dye, in both situations, our dye can be attached on the DBC board, but the connector will always fall directly after you take it out from the oven. And so we can conclude here, like the silver centering requires at least one of the touching surface to be silver plated, and both surfaces to be silver plated is recommended. So finally, after this experiment, we decided we will keep the silver centering for the dye attachment, which is the most important part, but for the connector attach, we'll keep on solder material. And then after the dye attachment, you need to do a shear test to make sure it meets the minimal shear requirements. Based on the size of the dye, the minimal dye attached strength should be at least 5 kilograms. And what we did is a destructive shear test in 4 different directions of the dye. And fortunately, they all passed the requirements, you can see. They all much higher than 5 kilograms. Yeah. And then is a thermal shock test. We use this thermal shock test chamber to test the mechanical reliability of the dye attachment using the military standard 83. We set the high temperature chamber on the top at 120 degrees centigrade and low temperature chamber at bottom at minus 55 degrees centigrade. And the test specimens are put still in one chamber for 2.5 minutes and rapidly moved to another one within 10 seconds. And this cycle is repeated 15 times. And after that, this is our results. So in this figure, the number with black background marks the 7 chips went through the shear test twice, before and after thermocycling. And the number with transparent background marked chips only went through the shear test after thermocycling. One thing I need to mention here is this time what we did is a non-destructive shear test. And the test load is set to be 5 kilograms, which is the minimum requirement. So non-destructive shear test means you try to push a die, and when you reach to 5 kilograms, you keep the force for about a few seconds, maybe 5 seconds. And if the die is still attached on the DBC board, it's passed. After that, what we did is a wear bonding and bond pull test. In the left-hand side is our kind of half manual wear bonder, and in the right-hand side is still the data 4000. For the aluminum die with 300 micrometer diameter, the minimum wear pull strength should be 150 grams. And this figure shows our testing results. And apparently they all pass, they are much higher than this value, so the tests are being passed. Okay, after all the tests, we can start to do our final packaging with the help of the 3D printer, which I use to print all the cases I need for the packaging. And we got our final module, which can be shown here, and we can also be showing here exactly the same. You want to have a look? And I also get another version which has a painting on the back. So for this module, the voltage rating is 1.2 kilovolts. The current rating is 100 ampere. So the power rating is 120 kilowatts. Yes. This is a comparison between a commercial model with similar power rating. You can say we reduce the size furthermore. And for the base plate, the size can be reduced as well. This one is designed especially to fit on our fans in our laboratory, which we already have. So we increase the size a little bit, but you can reduce the size furthermore of the base plate. Okay, now I think I will hand the speaker to the Robert, who will talk about electrical characterization.
Good afternoon, everyone. I'm Robert. I'm working with Winnie on this project. So Winnie has introduced the how a power module is made in our lab. I'm going to talk about the test we have done to characterize our module. So now it's stage 7, electrical characterizations. So firstly, we did this static characterization using a curve tracer. So I'm not sure if you, this is our power module on the test. So among all the tests, the output characteristics is what we are most interested in, which is just the drain current against the drain source voltage. This is a result at different gate voltages. So as is expected, when you have higher gate voltages, you will have lower on-state resistance. So the line will be shifted to the current a bit. So for this particular power module, when you have about 100 amps, you will have about 1.5 volt drop on the drain and source, which matches the datasheet of the die we used inside the power module. So we're happy about this. So next, we did this dynamic characterizations. We use this standard double pulse test circuit. Here is our half-bridge module. So we shorted the upper arm and we triggered the bottom arm. We measured the voltage across it and the currents. We test under different gate voltage and gate resistance. Here we show one of these results compared with a closely rated commercial silicon carbide module. So the dashed green and blue lines are the voltage and currents of the proposed module, and the solid gray and black lines from the commercial module. As you can see, the switching transient is much faster, and in terms of turn off, it's similar. So now we know that the proposed module can switch much faster than the commercial module. We want to know how much the energy can be reduced by using this proposed module. So we just simply multiply the voltage currents and integrate the power over time. So we get this calculated switching loss. So for the switching on and switching off at different currents, we got this comparison graph. So as you can see, for the switching on, we have just 1/4 to 1/3 of the switching loss of the commercial one. And for the switching off, we reduce the switching loss by about 25%. All right, lastly, we did this inductive load test, which in this test, we put our power module in constant switching operation. So this is the diagram of the test circuit. So with this circuit with limited active power input, we can have large AC current circulating in this loop. So this is one of the results at 600 volts DC link, and the current is 30 amps peak. We carried out different tests for the switching frequency from 5 kilohertz to 20 kilohertz, and the current from 10 amps to 30 amps and up to 70 amps. So all the tests were successful. That proves the power module functions properly. Yeah. All right, okay. That's a present from us today. Thank you very much. Any questions?